Hi everyone, this video we're going to be talking about loci in the Argand diagram, so complex loci. Now a locus is just a set of points that obey a particular rule. So these conditions could be anything from as simple as saying the set of points that obey the rule, let's have the set of points that's the exact same distance from one single point. So we could have that one. So that's a really easy one. So here's a point. I could say, what's the set of points that are exactly 2 centimeters from that point? So it would be that circle. Others are more complicated. If I have the set of points that's the same distance from a line and a point, I actually get a parabola, and that's the definition of a parabola. You can have the set of points that the difference between the distance between those 2 points is the same. So the difference is a constant, and you actually get something that looks like this for that one there. It's called a hyperbola. So there's all kinds of different geometric shapes and objects that we get based on basic definitions of locus. So that's what a locus is. There's 3 in particular that you need to know that pertain to complex numbers and complex loci. So that's what I'm going to go through in this video. First one is if we have the set of points the same distance from a particular point equals a certain value. So the distance in this case here, we're saying the distance, and the straight lines here mean distance. So the distance between Z and Z1 is equal to K. So that's going to be a circle centered at A with radius K in this case. So a particular example, the modulus of Z minus 2I is equal to 2. So this says what the length, what give us all the points that are 2 away, and we want to know the points that are 2 units away from the point 2i. So on here I would draw the point 2i, and I want all the points that are exactly 2 units from there. So we're talking about a circle that's radius 2 and they're at 2i. So we've also got certain points that we can see it goes through. So it would go through 4i up there. We could give these points here. So we can get pretty accurate here with this. And remember, this is an Argand diagram, so this is the real axis, and this is the imaginary axis here. In part B, we have to be a bit careful here. We've got the modulus of Z plus 2 minus I. When you're doing these, you must always write it in what we call the standard form. So you write Z minus negative 2 plus I equals root 5. Okay? Now notice, negative 2 is 2, negative I is negative I, so that there will give us the same as 2 minus I. The reason why we want to write it in this form here is I can clearly see that the center of the circle is going to be negative 2 plus I. So negative 2 plus I around about there, and the radius of the circle is still going to be the square root of 5. Okay, so the radius here is going to be about 2.23 odd. So this one here is a little bit tougher to draw really accurately, but the important thing there is getting this in that standard form where you've got Z minus, and that clearly shows you what point it is. That's the center of the circle. Here's the first one, and there's the second one. Second kind that you have to know is what we call a half line. So it's where I tell you the argument is a certain value, and because when we're talking about arguments, say pi over 4, that's not the whole line, we're only talking about a half line here. So here's an example. Let's look at A. The argument of Z minus 1 minus 2i, again, really carefully put it in this form here. So that's your first step here. Always get it so that it looks like that, Z minus that. So you can also check minus 1, yes, and minus 2i, yep, that looks the same as the top one there. So I can see now in this case that we're talking about a half line that starts at the point 1 plus 2i. So it starts at this point here, and the angle that it makes with that positive axis there is pi over 4. And that's, so the locus that I'm drawing is that line there, the solid line there. So every point on that line satisfies that locus. For part B, we've got the argument of z plus 2 plus I is negative 2 pi over 3. Let's look at the answer for that one. So writing it in standard form, we'd have the argument of z minus negative 2 minus I equals negative 2 pi over 3. So the point that we're starting at here is negative 2 minus I, that's where we're starting there, and the angle that it makes, negative 2 pi over 3 or negative 120 degrees. So the locus is this, this line here going off down here, all the points on that line there. The last one that you need to know is the set of points that is the same distance from two given complex numbers. So this is the perpendicular bisector of those 2 points. So that blue line there, every point on that blue line there satisfies the condition that it's the same distance from that point as it is from that point. Obviously the midpoint of the line is the same distance. All of these points here on this line satisfy that condition. That length is the same as that length there. Okay, so this one, the way that it looks, if we draw it, is something like this. The modulus of z plus 1, and I'm going to straight away put this into standard form, that's z minus negative 1, equals the modulus or length of z minus 1 plus I. Okay, doing it that way will clearly let you see what are the 2 points that we're talking about. So what this really says is we want, what's the set of points z where the distance from negative 1 is the same as the distance to 1 plus I. That's what this is saying in longhand notation. You just need to know how to write it like that. So we've got the points here. It's going to be negative 1 is one of the points. The other point here is 1 plus I. Here. And we're looking for all of the points that is the perpendicular bisector. In the exam here, you might want to, obviously you're going to bring a ruler. You could do this a little bit more accurately, but that would be a sketch of what the locus would be. Now, what if we wanted to know what the equation is? So let's go a step further now and actually work out what the equation of that locus would be. And we can do that just by saying, let me add a page in. We can do that just by saying, okay, let's say this point, this complex number z is x plus I, y. And I'll use x and y here because we're talking about the coordinate plane. So it's easy to think real numbers x, imaginary numbers y. On the left-hand side, we've got z plus 1. And on the right-hand side, we've got z minus 1 minus I. Okay, let's replace this with x plus iy. And on the right-hand side, we're going to replace z with x plus iy. Okay, a little bit of grouping here. This is x plus 1 plus iy. You can see what I'm going to do is get together the real parts and the imaginary parts here. On the other side, we've got x minus 1 for the real part, and we've got y minus 1, lots of I. Just check that that's right. yi minus 1i. That's good. Okay, so on the left-hand side, if I was to say, what is the length of that complex number? Well, the real part is x plus 1, the imaginary part is y. So thinking Pythagoras' theorem, it would look like this. On the right-hand side, doing a similar thing, the length of that complex number would look like this. There we go. If we square both sides, we could get rid of those square root signs, and then I can square out the bracket. So if I do that, over here I get x squared plus 2x plus 1 plus y squared. On the right hand side, x squared minus 2x plus 1 plus y squared minus 2y plus 1. Okay. Remember, this is algebraically showing what the equation of that locus is going to be. So let's do a bit of cancelling here. We've got x squared on both sides, so they're going to cancel out. We've got y squared on both sides, so they're going to cancel out. Let's deal with the rest. So if I add 2x to both sides, I get 4x. So I've dealt with those two. If I subtract 1 from both sides, it's going to get rid of those ones, but we've also got this 1 here, so we're going to subtract 1, and I'm going to add 2y to both sides. So actually just let's leave the 1 over there. There we go, 4x plus 2y equals 1. That's the equation of that line that we drew up there. If we get it in standard form, we'd have 2y is negative 4x plus 1, and y is negative 2x plus a half. So if I go back to my diagram here, that line there would be negative 2x plus a half, and it looks pretty reasonable from what I've drawn that that would be looking like the answer. Of course, if you had a situation with one of these complex loci problems, it might be that the x squareds and y squareds don't cancel out, in which case you wouldn't be one of these particular ones, but you could go through this exact same situation algebraically and then find out the equation of this locus just using the same method that I've gone through here. The other important thing to recognise is these same questions but just with an inequality sign. So if I say what's the locus set of points z minus z1 is less than or equal to k, I'm talking about all of the points on the inside of the circle, so not just defined by the boundary of the circle, but also the points inside the circle. If I say what's the argument z minus z1 is greater than or equal to alpha, let's say, so I'm saying here, not the points just lying on that red line, but all the values that are greater than or bigger than that line. Now, given that we always deal with angles between 0 and 180, really we're just talking about this region of the graph here. So it's a whole region there that this inequality gives us. And lastly, if I say the set of points that are closer to z1 than z2, and that's what this little thing here says, give me the set of points so the distance of z to z1 is less than the distance from z to z2, then we're shading one half of the line or one side of the line there. You can get questions where you get a combination now of complex loci. So in this one here, we want to, on an Argand diagram, we want to shade the region whose points represent complex numbers z which satisfy both these inequalities here. So we need to recognise that this one here represents a circle centred at 0 and a radius of 2. So that's all the points there. And this one here is one of the second one. It's not the argument one, it's the one where we're doing the perpendicular bisector. In this case, the perpendicular bisector is between 0, 0, that's this one here, so we're just saying the modulus is the length of points from 0, and let's write this one in standard form. So the right hand side is z minus 2 plus 2i. So in this case here, we're talking about the point 2 plus 2i, so it's this point right up here. So we're looking at what is the perpendicular bisector. It's going to go right through the middle there. So it's not exactly to scale, but you get the idea. So that's that blue line there. So let's now do the inequalities. For the first one, we're talking about all the points less than 2, so we're talking about all the points inside the circle. So that's what I've shaded there in yellow. The second one, we're saying what are the points that are closer to, in this case, the origin, 0, than they are to 2 plus 2i. So we're talking about all of the points that are on this side of the line. So now finally we ask ourselves, well, what are the set of points that satisfy both of those inequalities? So what's the intersection of those two areas? So hopefully you can see that we're talking about the points this side of the line and inside the circle. So everything in there are the points that satisfy both of those inequalities.